In this video, we're going to look at linear regression. So let's look at some basic ideas before we look at what linear regression is. Scatter diagrams and correlation. First of all, responsive variable, which is also known as dependent variable or the y value on the x and y graph, is a variable whose value can be explained by the explanatory variable or predictor variable. So this is also known as independent variable or the x value on the x and y. So if we have x and y, this is the independent variable or predictor variable. This is the response variable, the y. Scatter diagram or scatter plot is a graph that shows relation between two quantitative variables measured on the same individual. Each individual data represented by the point in a scatter diagram. Okay. So like I said, the predictor or explanatory variable is on the horizontal axis and the responsive variable is the vertical axis, the y value. So here's an example. Okay. So the left side is the data in table showing based on a study on drilling rock. Researchers want to determine whether the time it takes to drill here's a key point, to drill a distance 5 feet in rock increases with the depth at which the drilling begins. So essentially, is deeper the rock, does it take longer time? Are we curious? So the depth at which drill begins is the explanatory variable, x, and the time in minutes to drill 5 feet is the response variable, y. So here's a scatter plot. So scatter plot, so for example, for depth 35 feet, somewhere here, it took about 5.88. For depth 50, it took 5.99, that's where this point right here. And for 75 depth, somewhere here, it took about 7.4. And we do this for all the plots. Okay, so you can think it's an x and y coordinate. This is 35, 5.88, 50, 5.99, and we'll do this for all the points. Okay, so this is how we plot a scatter plot. And scatter diagram can exhibit three types of relationship. You can exhibit linear relationship, a non-linear relationship, or no relationship at all. There's three types. And in our class, we're going to focus on linear relationship if it has a relationship. So we're going to see how to determine if there's a linear relationship or not, and how can we use it if we have a linear relationship. Okay. So for example, if the scatter plot looks something like this, for now we're going to rely on the visual. If the scatter plot looks something like this, we have a linear. So this linear means that we can draw some kind of a straight line to fit the data pretty well. I know we're kind of using very subjective way to describe this pretty well, but just bear with me for now. There's a way to actually measure this numerically. So explanatory is also linear, because when one is increasing, one's decreasing, but still we can form a straight line. Again, even if we have something like this, let's say scatter plot looks something like this. This we can say, oh, this is pretty linear because we can describe this one line. Okay. And here we have a non-linear. So this is some kind of relationship, but non-linear. But it is a type of relationship, right? This is non-linear, some kind of relationship. We don't know, we were not looking at that in our specific class, but only thing we can determine is non-linear relationship, but some kind of relationship. And this one, no relation. There's no visible relation in this case, in this kind of graph. Okay. So, in terms of, since it's a linear regression, we're going to focus on how to identify first if we have linear or non-linear, and if we do, how we can use it. Okay. So, first, two variables that are linearly related are positively associated. If whenever the value of one variable increases, the value of other variable also increases. So when x increases, maybe y increases. X increases, y increases, and so forth. Then we have positively associated. But the key idea here is that if two variables are linear, we already determine this linear. Then we can also determine is it positive or negative. So if it's two variables are linear, we can determine are they negative associated. That means when one is increasing, other is decreasing. One is increasing, other is decreasing. So we have some kind of this straight line describing the data. Graphing a scatter diagram. So there's several ways of graphing diagram using technology. In our class, we're going to use the online calculator. So for this, please look at part 2 of the video. And I'll be also doing all the example problems in this video using part 2, in part 2 video. So make sure to watch part 2 video after this. This video is more going into the concepts. Okay. So how do we determine such a relationship looking at data? Even without looking at actually scatter plot, we can determine numerically if we have linear or nonlinear relationship. And that's called linear correlation coefficient. Let me use highlighter. And that number is called actually R. That's the R value. It's a measure of a strength and direction of a linear relation between two quantitative variables. And we use this formula to find it. But again, in our class, I'll demonstrate how to find this using an online calculator. But in this video, we're most going to focus how to interpret this R value. There's difference between what R value is versus how to find R value. How to find R value using this formula is just using a calculator, which I'll show you in part 2. Okay. But just to summarize, just to explain the formula so that we know that these are not just random formula, we're finding that each data's distance away from its mean and divide by the standard deviation. Same thing for the second variable also. Okay, we do that for all of them and multiply sum of all of them and divide by n minus 1. Okay, so that's what we're doing. So we're using the mean and standard deviation, sample standard deviation of each x and each y variables. Okay, so here let's talk about how to interpret this R value. Okay, that's the main focus of this part 1 video. The linear correlation coefficient is very important. This important facts regarding are follows. So these are all the characteristics of R. The linear coefficient is always between -1 and 1. That is -1 greater, less than or equal to R, less than or equal to 1. Okay, so let me just write it in one line. It could equal to 1 or -1. It's always between these two values. You'll never be 2, never be 1.2. It'll be always between these two numbers, including -1 and 1. So let's look at the interpretation. If is exactly +1, then we have a perfect positive linear relation between two variables. So that means we have a straight line, something like this, and all the scatter plot points are on this line. If it's +1. If it's -1, then we have a perfect negative. Okay. So it's not always going to be exactly 1 or -1. A lot of time it will be decimal between 1 and -1. The close to R is +1, the stronger the evidence for positive position between two variables. So if you get 0.9, 0.999, or even 0.7, 0.8, that means we have a close. We have a scatter plot that can be described by a straight line in positive direction. Close to -1, stronger negative. Stronger evidence of negative association between two variables. Okay. If R, this is important also. If R is close to 0, then there is literally no evidence of linear relation. It could be some other relation as we saw earlier, like some curve or parabola. But if it's close to 0, such as 0.05 or 0. Even 0.1 or -0.01 or -0.002, those are as numbers close to 0. So you think as a number line. Here is 0, -1 and 1. Closer to 0, no linear. Close to 1, strong positive linear. Close to -1, strong negative linear. So linear correlation coefficient is a unitless measure. There's no unit. The correlation coefficient is not resistant, therefore observation that does not follow overall parent data could affect the value of of the linear coefficient conservation. All this is saying is that if we have an outlier, let's say I have an outlier that is really large or really small, it could affect it by that a lot. Okay, just like the average, because we're using the mean value, the mean values are not resistant here means it could change a lot depending on the outlier. And the one idea that we saw that is resistant to outlier was the median value earlier in the module, right? Or earlier in the section in our class, right? So let's look at some examples with the corresponding graph and R value. So if R is exactly 1, we have a perfect straight line that describes the data, fits. If R is close to 1, such as 0.9, then we have a strong linear positive. Again, two things, linear relation and strong positive. The linear coefficient R gives us two ideas. First, is it linear or not? And if it is it strong or moderate or weak? Okay. Here, moderate positive, 0.4. So you can think as here 0, negative 1, 1. 0.4, yeah, we can think that 0.4 is more positive. And it's moderate positive. Straight line can fit here, but still, data is somewhat scattered, spread around the straight line, right? So we can say this is a linear relation. Now it's negative 1, perfect. Close to negative 1 from the left side. So negative 9 somewhere here, or right side, I guess. Right side of negative 1. Strong negative. Not perfect negative, but strong negative. Negative 0.4, moderate. Right? If it's close to 0, then again, there's no line that can describe this data very well. Right? So this will be close to 0, and it will be something like 0. Even 1 or even 0.03, something like that. There's no straight line can describe this, right? So we shouldn't just assume that just because positive, that means there's linear. This is not linear. There's no relation linear, no linear relation. Some other relation, but again, in our class, we're looking at just no linear relation. Okay, so just to show you, this is how calculation works. Again, you will not need to do calculation this way for us, because our focus is to learn the concept of linear correlation coefficient in our class. But this is how it is calculated. So we're finding distance between the mean and its value, divided by sample percent deviation for all the values, multiply them, and divide by n-1. Okay. Again, I'll demonstrate this in part 2, how using an online calculator. But right now, focus on how to interpret R and we're going to see how we're going to use this. So for this data, whatever this data is, this is the rock drilling data we looked at earlier. Okay. For the rock drilling data, even without looking at a scatter plot, we can see that R is 0.773. So without relying on a scatter plot, we can determine that since R is fairly close to 1, data exhibits moderate to strong positive linear relation. So 0, 1, and negative 1. R is here for this example. Here's R, 0.773. So close to 1, there is linear. And because this number is positive, is moderate to strong positive linear relation. So telling two things. Okay. Again, we'll not be calculating by hands. We'll be using a graphing calculator, but specifically online graphing calculator. Okay. So for now, just focusing how to interpret R. Okay, so no need to worry about. Some of you may have graphing calculator. Then you're welcome to follow the steps. But I think in part 2, using an online graphing calculator, I think it's a little simpler. So again, I'll do this example 2 in the part 2. So we determine R value. Okay. So R value tells us, first, is there a linear relationship? And if it's yes, then it tells us, is it positive or negative, with what strength? Strong, moderate, weak. So then what we can do is we can do least square regression. If there's a linear relation, we can find the best fit line equation. Okay. So this is where we use this idea of linear equation. Maybe you heard it before. If not, let's review it. Recall how to write equation line that fits set of data. Using the data below, we can write a sample linear equation that relates to x and y. So this is where we use the idea of slope. slope and y-intercept. So we find the slope between 2 points, rise over 1. So if I pick between 2 points, I find distance between y, and I find distance between x, and divide by to get a slope. And I use a slope intercept form, and I plug x1 and x1, and I get this equation. So this equation is a linear equation that contains these 2 points. Okay, so the relation you create can be used to predict value of y instead of, or based on x. Okay, so in this data, we have x equals 0, 2, 3, 5, 6, and 6. Okay, and if I want to find, for example, like 2.5 or 4, I can use this equation to find a prediction, not guaranteed value prediction. And that's the idea of linear equation. Okay, so we're going to learn how to come up with this equation. Well, actually, we'll be using the calculator to come up with this equation, but we're going to learn how to use it. Okay, so for now, just know that we're going to use linear equation, slope and y-intercept form. Okay, so going back to the scatter plot idea, which is just a data set in a scatter plot, observed value or response variable comes from the original data set, and the information you're given is given from observed, because we observed the data. Predicted value of a response variable comes from prediction. So we're trying to make a prediction with our best abilities, of course. Prediction value is obtained by substituting given value x into the linear equation. Okay, so like in above this example, we could plug 3 here to predict it would to be 4.75. But actually, the observed value when x was 3, it was 5.2. According to data, when x was 3, the y value was 5.2. But prediction says 4.75. So there's some error there. Okay, and that error is called residual. The difference between the observed value y and the predicted value y, denoted as y hat, because it's prediction value. It's called the error, which is we call it residual. Okay, so for instance, using the observed and predicted value at x equals 3, there's some residual here, as we talked about. There's the difference. So for this data, we have a residual of 0.45. And we're going to have a residual in many data because we cannot fit entire scatter plot dots into one straight line unless we have a r equals perfectly positive 1, perfectly negative 1. Right? So we're going to have a residual in many cases, in many real data. And our goal is to find a line such that we have a smallest amount of residual. And that's where the idea of least square regression line comes. While our goal is here's a residual, right? Here's the error, here's the error, here's the error. We want to minimize this error. Okay? So the least square regression line is also known as quote unquote best fit line. So when you hear the best fit line in regression, we mean least square regression line. So we're actually defining the best fit. Best is not just, oh, it looks better. That's not what best is. Best is mathematically, we want to reduce the residual. But specifically here, we minimize the sum of the square error. So we square all the errors, and we want to minimize that. We want to find this equation a straight line such that it will minimize the sum of square error, square residual. The line that minimizes some square or vertical distance between observed value y and those predict y hat. Okay. And this is the equation. Again, this equation we'll be able to find using the calculator in part 2. But for now, just focus on how we're going to use this. This equation, we use y hat because that's the predicting. We're trying to predict y value. So for in this data, I would like to know the y value when x is 6.5. But that 6.5 is not observed data. We did not observe the data. We did not collect that. We don't have that data available. But we can predict it by using the equation, and I can find the corresponding y value. And that this y value will be predicting value. It's not guaranteed, but predicting. And of course, stronger the R is, the more reliable least square line is. Okay. So again, here I describe how to find it. Is using the R value and the standard deviation. But again, you will not be finding this equation by hands. It's more focusing on how to use it once we find the equation, or once we have the given equation given, linear regression line given, least square regression equation given. So here we obtain this equation using the formula or a calculator, or it's given in the problem. So this is the drill rock drilling example we saw earlier. So it's a linear regression line. Okay. So again, the graphing calculator or online calculator that I'll be doing in video 2 does this for you. Okay. So this right here, we found this data. This is the equation. This equation, let me write here. Let me write this equation. This equation of this line is y hat equals 0.0115x plus y-intercept of 5.5326. So this is the best fit line. And the way we define best fit line, just understand what it is. Okay. Here we have an error, right? This is the residual between the equation and the actual observed data. We found the line such that if I square each of these number distances and add all of them, I got smallest one. I square each of these distances and I got smallest one. And that's what the least square line is. Okay? So least square line, the definition is best fit line. Essentially, we want to minimize the square residual from the observed data and predicting data. So the reason this is useful, especially for linear relationship, this one is somewhat moderate or strong because we have 0.7. 7 is the R value earlier. And if you remember, the R for this was 0.77. So if I want to find, okay, if the drilling depth was 110, which is not in the observed data, I can predict using this equation line. Then I find, okay, they'll take about maybe 6.8 minutes. And I want to predict, okay, how about 170? It's not observed data. I can find predicting maybe 7.5 minutes. So this equation can be very useful predicting the values that we don't have access to from collecting data, or even future data, right? In terms of time, if the independent variable is time, I like to predict certain y value. And it's not always reliable. The reliability is stronger as this number is bigger. We can always come up with a linear equation no matter the data. Even the scatter plot that doesn't have linear relationship, even something like this, we can still find an equation somehow using the calculator or using the formula. But then this line is just not reliable. That's why this R value we talked about is so important, how to interpret R. Okay? So this is the end of the part 1 video.